Welcome to Math 2318, Section 4.2. In this particular section, we're going to look at things involving the null space, the column space, and the image of some linear transformations. Alright, so in question 1, we have a W. We want to know if that's in the null space of matrix A. Well, that's pretty easy to check if it is or it is not. We look to see, is it true that A times W is 0? So A is 3 by 3. My W is 3 by 1, so the multiplication makes sense. The answer will be 3 by 1, and so you simply perform the multiplication and see if it's true or not. And in this case, yes, W is in the null space of A because A times W is 0. Alright, so in question 2, we have matrix A here. We want to figure out, well, what does the null space of A look like? Can we find the set of spanning vectors? Alright, so, well, first off, I want to figure out, well, what do all the vectors look like in the null space? I'm trying to solve AW equals 0. So here's A, here's the 0 on the right-hand side. We do our row operations, which are pretty easy. All I have to do is use this 1 to make a 0. So at that point, what do I see? I see x2 is minus 4, x3 plus 7x4. And I do the same thing to find x1. So that characterizes for me all of the w's where A times W is 0. Then it's just a question of splitting it up into things that have x3 in it and things that have x4 in it. So here's the x3 stuff, here's the x4 stuff, which gives me a characterization for the vectors that span the null space of A, because every vector in the null space is representable in this particular format. Alright, in question 3, they give us a particular subset of R3. They are vectors of the form R, S, and T, but there is a relationship that must be true about R, S, and T, and that is given here on the right hand side. So if this is going to be a vector space, well, it has to be a subspace. That's certainly true. It has to have the 0 vector in it. So I want to know, is the 0 vector in W or not? Well, let's see. Can I get 0, 0, 0 to ever occur? And that is no, because of this relationship that they gave us. That would say minus 3 equals 0. So clearly 0 is not in there. Alright, so 0 is not in there. So it is not a subspace, pretty clearly. Alright, what about question 4 here? We have matrix A. I want to find out something about the null space and the column space. Well, let's see. What's the size of A? Well, it has 2 rows, 3 columns. That means that if it's going to operate on something, it has to operate to match this up. So it has to operate on a 3 by 1. Alright, so that means the null space, the dimension of the null space of A must be 3. And where's it going to? Well, if it's a 2 by 3 multiplied by a 3 by 1, My answer is 2 by 1, and so I get that the dimension of the image or the range is going to be 2. And that's all they wanted us to find out over here is the K, where it would be a subspace of RK. It's just a question of looking at where we're going and where we're ending up. Alright, so here we have matrix A. So I want to figure out if W is in the column space and if W is in the null space. Well, let's see. If W is in the column space, then I should be able to find an X where AX would give me W. Alright, so here's A, here's W where I want to end up. I do row operations to figure out what happens, and so I get this particular relationship. And so what that says is if I let x2 be 0, so what that says is the x that should work is this particular x minus 1/3 0. A multiplied by it, if you check, does give you 3, 1. So yes, W is in the column space of A because something does get mapped to it. Is W in the null space of A? I don't know. So take A, multiply it by W, and see if you get 0. And well, yes, we do actually get the 0 vector. Now they say something silly here, and that is they say a vector that gets mapped to W is 8, 3, 1. Well, that cannot be the case because A is 2 by 2, and a 2 by 2 could not be multiplied by this 3 by 1. So not sure where that came from in their solution. All right, in question 6. In question 6, it's an interesting question. We have a linear transformation mapping the collection of second-degree polynomials into R2 by this transformation. All right, so first off, what's going on here? So if I take a polynomial in P2, it has to be of this form for second degree. So what about P at 0? Well, P at 0, that's 0, that's 0, is just a 0. So that says that T of this polynomial as they defined it is P at 0, P at 0 repeated, which says that T of the polynomial is simply A0, A0. So that means that the range of my particular transformation is the collection of all things in R2 of the form AA, where A is any real number. So all the points along the diagonal line, including the origin. What about the kernel? Well, what can we say about the kernel? What items get mapped into the origin? 0, 0. So let's see, T at the polynomial must be 0, 0. So what that tells me is A0 must be 0. And if A0 must be 0, then it's all polynomials second degree of this format, which if you look at that says that the spanning set is P1 of T is T and P2 of T is T squared, because everything in the kernel is a linear combination of those two vectors.